Welcome. In this lecture, I want to go through kind of special kinds of rings. So these are actually most of the rings that you've dealt with. Well, okay, no. So the real numbers are going to be our classic example of fields. For commutative rings, it's going to be the integers. Okay, so all rings. Oh, let's make that red. I'm into making everything having to do with rings red, and we'll probably continue that throughout. So all rings have commutative addition. Right, and you can recall that that's saying that A plus B is the same thing as B plus A. Right, when I add things, the order I can switch it, it doesn't matter. Okay, and then, but some rings also, as you have wanted to believe from the start, because your first example of a ring was the integers, that some rings also have commutative multiplication. And now I put a big sum there. And before you ever get carried away with thinking that everything is a commutative ring, remember that multiplying matrices, the order matters. Okay, so what is this? So definition. Okay, so a ring R plus multiplication is called commutative. So is called commutative okay, so when is a ring a commutative ring? Well, it has something it has to satisfy. And so it's going to be commutative if and only if the multiplication, right, which you're denoting by x there, is commutative. Okay? Commutative ring. A ring, all rings addition is commutative, but if multiplication is additionally commutative, then it's a commutative ring. Okay, so our favorite first example is the integers, our favorite first non-example. And we'll talk a lot more about this, but this is M2Z, right, which is the set of all 2 by 2 integer matrices. Okay, so this is the set of all 2 by 2 integer matrices. Okay, now, so already some rings are going to have this commutative property, but sometimes we want them to even be more. So maybe we'll make it, no, we're going to make it green. Even though I was using green there, we're going to make this because like a field, like with deer and bunnies is green. Okay, so by definition, okay, so for the real numbers, even more is true. Okay, so for R, even more is true. And they're going to be a field, which I'll say what that is in a moment. Okay, so now let's say what that is. So definition. So a field is a commutative ring R. So a field is a commutative ring R So if I ask what kind of object is a field, it's a commutative ring, or you could even just say a ring. You know, this is another adjective on there that is commutative, but it also has stuff it has to satisfy. So it's a commutative ring, R, so that, and we have every non-zero so every non-zero element in R, so R is what the field is. So every non-zero, A and R. Actually, every time I rewatch, I hate that I don't just erase things fully. So every non-zero, A in R, is a unit. Okay, so let's just kind of focus it. So this is the definition, but there's a lot of stuff going on in here, so let's kind of parse it. Okay, so what is the type of object we have going on here? So this is the fact that it's a commutative ring R, or you might even just, excuse me, a commutative ring R, or you might even just say R. So this is the type of object. Right, and it usually has, and it's something that has to be verified, and you need to know what kind of thing it is. You know, something can't be a field unless it's a commutative ring, but it also has to satisfy other properties, so let's look at each of them. Okay, and so we have that it has to be, so now, what must it satisfy in order to be a field? Okay, so what it must satisfy in order to be a field, so this part is, right, what the commutative ring R must satisfy in order to be a field. Okay, and okay, so now we have something else I want to highlight in here, which is that it's actually necessary, right? And so this property actually has to do with certain of the elements are going to have to satisfy certain properties. And in particular, we're going to look at every non-zero element. Oh dear. I didn't use it for so long here that it just kind of, it's had it with me. So let's kind of focus in on the non-zero part. Okay, so this is actually necessary. Zero cannot be a unit, okay? And remember, just to remind you, a unit is something that has a multiplicative inverse, okay? So what we're saying, so what is a field? It's a commutative ring, okay? Commutative ring, multiplication is commutative. Addition is always commutative. In a commutative ring, multiplication is also commutative, okay? So what is a field? It's a ring where multiplication is commutative and every non-zero element has a multiplicative inverse. Okay, so this is getting us close to multiplication having all these properties that addition had. Okay, And then our favorite example is probably the real numbers, but there are other important examples, and you want to be able to talk. You can start doing linear algebra if you have a field to work with, right? You always have to have a field that you're working over. Okay, so I hope this made some sense, and I will see you in the next lecture.